doing his job with vessel accounts. And he is working on very interesting kind of project, particularly in communication theory. And this talk is also very interesting. So noise can be researched. So,
Thank you, Manika, for introducing. So, what today what I will discuss the notion of noise. So, I am audible, right? The notion of noise means, let's say when we are trying to send some information from maybe through some classical channel, maybe when you are giving a phone call to your friend. So then, if the channel is noisy, then your friend cannot uh, hear. I mean, if the noise increase, then your friend can, I mean, cannot completely cannot hear anything. So, but here we will show that this notion of noise can be actually that depends on the context. Means, what do I mean by context is that the accompanying resource. If let's say if we are in the quantum communication scenario, then the accompanying resource can be one LOCC or can be two LOCC. LOCC means the communication is from the CC means classical communication is from sender to receiver, or also there may be some uh, feedback from the receiver to the sender as well. So that depending on the communication context, so sometimes we will see that noise can also help in communication. I mean, let's say if we have, I mean, in classical sense, we know that if it is a noise, then it is always noise. If you increase noise, then it is the information will always decrease. But in quantum case, this noise, some noise parameters, if we increase this, this can the communication rate can be increased. So this is the main theme of this talk. So okay, so I am from this OIST, which is at Japan, but it's near Taipei. So actually here it is Singapore. So it's closer. I mean, it's from mainland with a distance, and from here the distance is almost same. So so yeah. So, and this has a nice greenery campus with more than 90 units. And actually, I am supposed to present the institute. So yes, that is also was a rule. So I just put this slide. Yeah, so this work has been done jointly with Aditya, which now with RWT Village Aachen with Mario Barta, and Sergi, who is Royal Society fellow at University of Cambridge, and David, who is my postdoc mentor there. Okay, so the content of my talk is like that. First, I will try to give the background, means whether there is some kind of contextuality already there in communication scenario, and what is the, I mean, the capacity of a channel, the information transmission capability of a channel, and many things. And then I will discuss some basic concept on the channels, so which will be used for to, to follow the work. And then in the result part, I will mainly show that what is our channel, how we constructed it, and then we will analyze its one-way and two-way capacity. And we actually our channel is for some certain region of the parameter, this channel is degradable, and outside the channel this will be anti-degradable. So not anti-degradable, it is beyond degradable. So I will show what is degradable and anti-degradable. And then I will again analyze this one-way and two-way capacity beyond this degradable range. And this is also same things for I will analyze for secret key distillation and distillable entanglement. And then I will show some classical wire tap channel and its one-way and two-way capacity. And finally, I will conclude. Okay. So the background is that, so if you want to try to estimate the information transmission capability of a channel, then it is in general a very tough task, because one needs regularization over a unbounded number of channels. Means for classical channel, actually from it, the result from it, the result is from uh, Shannon itself, that this feedback means if you are for the classical channel, if it is if there is feedback from the receiver to sender, then there is no advantage for the classical memoryless channel. And there are many issues are there. And also that, um, okay, so let us go step by step. Okay, so usually the information transmission capability of a quantum channel is very hard. Although for classical channel, only one quantity is sufficient because this the entropy quantity which actually characterizes the capacity is additive. Means you use of the channel or two of the channel, this will just sum. So when you calculate the capacity, you just average over it, and this is same because it is additive. But if you try to calculate the capacity of a quantum channel, then you cannot easily compute for in general. Means for some easy channels, for some class of channels you can write, but in general it is a tough task because because there is a concept of superadditivity. Superadditivity means this the in order to calculate or compute the quantum information carrying capability of a channel, this underlying quantity, this what you will calculate is the core information, and this core information is actually superlative. So it was first Davidson Joitel in 1998 who showed that for two use of the channel, for three use of the channel, this capacity, this core information actually increases. Increase means just it is not, let's say your core information is one, it is for two use, it is not just by two into one, means it's more than two. So for that, usually means even there is some result that even some unbounded number of channel use may be required. Means there are some result that for nth use of the channel you can have still zero core information, but suddenly for n plus one use of the channel you can have finite amount of core information. So in general, the computing the information carrying capability of a quantum channel, one need to regularize over infinite number of channel use because you don't know which n you can have the capacity. But there are
Nth use of the channel means you are taking n copy of the channel.
yes.
Okay.
Yes. Okay. So then this is the superadditivity of what I am saying was superadditivity of core information. But also there are some although Winter in 2016 defined some concept called potential capacity, but the main idea was from 2007 itself by John and Smith and Yair. So this was that okay, you have one channel which has zero capacity. You have another channel which has also zero capacity, but when these two channels are used together, you can have some finite capacity. So then this Winter proposed the concept of potential capacity of a channel, which is the maximum information carrying capability of a channel when it is used in combination with an auxiliary contextual channel. So in some sense, this is also this capacity is also contextual, means what auxiliary channel you are using. This will show also that after some slides that this quantum capacity is highly contextual. Means there is some channel what I was just saying that zero quantum capacity but positive potential capacity when it is used with some another auxiliary channel. So for our task, okay. So what I was saying that in contrast to classical case, because it is possible to consider a host of scenario for presence of different resources because in classical case or that means for the classical memoryless channel Shannon shows that actually if you have along with the classical channel if you have forward communication then it's fine but if you have reverse communication actually when you are saying the classical channel and there is no meaning of forward communication it means classical communication the channel itself is classical. So, but if you have reverse or feedback from the receiver to the sender, then you do not have any advantage. That is for from channel itself. Okay, but for quantum channel, we will show that we will consider the classical communication either from the sender to receiver or bidirectional means feedback. We will allow the feedback. Then I will show. I mean, for our case, the this this contextuality is in that scenario that this whether this auxiliary resource is one-way classical communication from the sender to receiver or two-way classical communication from both sender to receiver and receiver to sender, and we will consider the transition of quantum information and private classical information. That two quantities we will use. Means quantum information means you are trying to send some quantum state to a channel, and private classical information means, okay, I will show this. Okay, so this is the usual communication scenario. So there is one sender and one receiver. So it was first proposed by this paper by Lord Shannon in 1948. So there is a sender, receiver, and in order to send some message, the sender will encode this message, and then this message will be transferred to some channel, and then the receiver will record this ciphertext, and then he will decode and he will got the message. And you can think of this classical phone call. Your phone, your voice is transferred to some electromagnetic wave, and then it's transferred through some optical fiber, and then it will get decoded at the receiver end. And okay, but for quantum, what is quantum channel? So quantum channel is mathematically designed as completely positive and trace preserving map, and it takes some valid input state and it outputs some valid density matrix and it outputs some valid density matrix. So mathematically in Clausius representation, we can write down as ei rho ei dagger, where ei are the clouds. For the time being, let's forget about clouds. So, but this action of the channel on a quantum state, it has certain property that is, it is linear. Means if the channel acts on alpha rho 1 plus beta rho 2, it is alpha e rho 1 plus beta e rho 2, and it preserves the hermiticity, and it preserves the positivity. Means it takes all the positive density of is positive, means positive operator to positive operator, and it preserves the trace as well. That is, you take whether the trace before the channel action and after the channel action, it is same, and it is completely positive. Means if you took the extension of the channel with some identity or some k, let's say it is k dimension identity, then it should be greater than 0, and it should be greater than for all such k, for k dimension natural number. And it has another representation, so which is more convenient to think of, that let's say you have a sender A and a receiver B, but when you are trying to send some information from here to there, actually some this row can be affected by some noise, and so some information can be leaked to environment. So this is called channel, and this is called complementary channel. And what is the channel action? That is actually the overall unitary is actually an unit. Overall action of the channel is a unitary, or you can think of in more general way as a isometry. That means you allow all the higher dimensional things as well. So the overall action is isometry. Then you just if you apply this isometry on a initial state row environment, initial state of the environment, and initial state of the state of the system, means the sender. Then you took the isometry, and then if you just trace out the environment part, you will get the channel action, and if you trace out the system part, then you will get the action of the channel of the complementary channel. So these are the scientific representation. Okay. Now, how good a channel is, how to comment that whether a channel is good or not. So for this, you need some quantifier. So the information carrying capability of a channel, actually there are several kind of such for quantity. So that depends on what kind of information you want to send. So let's say we want to send some classical information. Means let's say you have some classical random variables, classical x1, x2, x3, which belongs to some set of some random variables, and you want to send this x to the receiver. So then what you will do, since it's quantum channel, you will just encode this x in some row x, and then you will send to the channel, and then you receiver will got. So this is the classical information. You are trying to send the classical information, and for this classical information, okay, one thing is that there may be n number of channels. Means there may be, you can actually, when you are trying to compute the information carrying capability of a channel, you are allowed to use that channel n number of times, n times to infinity. Because I mean, and in the representation version, you can compute that. Okay, this is the, you can average it and you can calculate. But also you can maximize. Okay, now let's say what is this information? This is actually hollow information. So that this Holloway information was this information was first introduced by Holloway and then by Schumacher and Westmoreland immediately after. Sorry, first by Schumacher and Westmoreland and then Holloway. Or I don't know, means which one is first after, yeah. So this Holloway information of a channel N is defined as this way, that you just calculate the this Von entropy of the channel and this what you are doing, you are encoding on some rho I, and these rho I are distributed with some probability pi, and you calculate this Von entropy of this channel at the axon of the channel of the overall state and minus this pi h of n to y, and this is the Holloway information, and again you have the independence to encode over all possible pi rho I, and you maximize over it, and then you calculate the classical capacity in this way.
What is capital N?
A capital N is the channel of which we are going to calculate the capacity.
What is PI?
Pi are the distribution of the your x randomly.
You progress with that also.
That's also that is on your hand in production. And what is private?
Maximization of PI.
And what is private capacity? It was given by Devata. So private capacity means what information you are trying to send privately to the receiver, so that the eavesdropper or someone else cannot learn it. So it is just defined in this way that you just calculate this Holloway information for n minus Holloway information for the complementary channel, and then again you can maximize over all possible encoding scheme, and also you can use n number of channel use, and you can optimize for all.
So it is not Holloway minus maximization of the different one.
Okay. So maximization is for this and for this.
Full total maximization. Not rate is no.
Okay. Yeah, but because encoding is once. Yes.
Oh, maximization this minus maximization this.
It not to be maximization of this minus maximization.
Yes. And what is quantum capacity? So now you want to send some quantum state instead of classical information. So in order to do that, the underlying quantity is core information, which is just age of n row minus age of n bar row. M, what I had already defined what is n and n bar. And again, you may maximize over all possible encoding of the state, and you have to calculate over the in the regularized version. This will by Lloyd Su and Devata. So what I was mentioning just few minutes ago, that actually capacity depends on context. Such kind of results are already there. Means this is called the superactivation phenomena, which means this is by Speed and year in 2007, right? 2008. Okay. So there are two channels, N1 and N2. So let's say this is N1. So this sender want to transmit this quantum state to the receiver, but this has zero capacity. And also there are another channel which has zero capacity, but when they are used together, then they can send at least with some non-zero probability. So that kind of at least existence is there. Non-zero world. So this communication capacity of this channel also depends on the underlying with the assisting channel. So that depends on the context. Okay. So let us then now discuss some known concept of channels. Okay. So degradability and anti-degradable. So what is degradable and anti-degradable channel? So let's say we have a channel N from sender to receiver, and we have a complementary channel from sender to the eavesdropper. We have already defined this earlier, that the action of the channel is that we have to trace out over the environment part, and in order to calculate the action of the complementary channel, you have to trace out over the system part, so the receiver's part. Then you will get the action of the channel and complementary channel. Now, a channel is called degradable. This N is degradable if it can be degraded to NC. Means there exists a CBTB map T from HB to HG such that this T, when this T acts on N, it can simulate NC. So that is the concept of degradability. Means N can be degraded to NC. And what is anti-degradability? Anti-degradable channel. So the complementary channel is degradable. Or you can think of that there is another map S from environment to HS to HB such that this N can be simulated as from the NC. So there is another concept of degradable state by Levitsky and other people. So actually this is nothing but you just take the bipartite state rho AB and you take its which is some purification phi AB. it is called degradable if and only if there exists a channel RB, means B means from here to here, B to E, such that it is I mean, the same concept, but you can now think of in terms of choice state. Choice state means that you just take the identity and then there is a lambda over a maximum index. Anyway, you can think of that there exists a channel RB which when act on the row AB can simulate row AE. Where you can also where rho A actually you can calculate from tracing over the phi AB part also. Means rho A you can calculate from here by tracing out B, and also you can calculate from rho AB by acting on this map. So this is called degradable state. Actually, these two concepts are almost same. Means actually the choice state of a degradable channel is a degradable state with the same degrading map. So you can just say same. In identity, it is actually identity tensor R.
In this meet, we are meet with the
Let it give me dot probably.
2012.
Quite
Not very old.
later. Okay, so now I will introduce actually there are, but I am just going to introduce this because I will use it after some time. So almost anti-degradable channel means the channel now I told what is anti-degradable channel.
Can you just this degradable state is not clear.
It is, let's say you have a state
For any state it is defined whether or not. Okay.
No, a bipartite state will be called anti-degradable if it is satisfied. A degradable if satisfied is proper.
Or the
If
purification.
state, if it has a purification.
Ah.
Now, if there exists a RB such that action of RB on rho AB, you can actually think from tracing out this B part on the purification.
Means actually there is an identity here. Identity is identity on A.
So but RBE means it's a channel from B,
B to E,
Oh,
yes,
okay,
yes.
okay.
Actually,
Understood.
yeah.
So now you are saying that if I have a channel which is degradable, then the CHOI of that channel will be a degradable state,
Yes, yes,
and the other way also.
yes. So then what is almost anti-degradable? So you have a quantum channel chi from A to B. It is said to be epsilon close anti-degradable if the distance of the state from some eta, where eta is an anti-degradable channel, is bounded by epsilon. This diamond norm of chi minus eta is bounded by epsilon. It's called epsilon anti-degradable. Now, what is this distance between chi and eta? Eta is an anti-degradable channel, and this is a diamond norm. So, diamond norm,
Will be there some optimization.
yes, this is optimization.
For all possible
definition it is
degradable
defined.
channels.
So, this diamond norm is defined in this way that you have to extend this chi as well as this eta by identity for A, and you have to optimize and you have to calculate the trace norm. Trace norm is usual trace norm is root lambda root whatever row and trace norm, and you have to optimize over all possible n. So in general it is very difficult to calculate. And the trace norm of a channel means it is a trace norm of the channel. It is not state. The trace norm of the channel is you just act on a some state row and then you can maximize your row. And yeah, so this is the so now it should understood.
Means like you were talking about the eta optimization.
So that is not required. There is
Because there should exist
There
integration.
You are talking about eta optimization.
there should exist a eta such that this
Becomes
epsilon
epsilon.
epsilon condition is satisfied.
Okay. Yeah, no, but this epsilon can be large. Means I mean, if you say that epsilon is very small, then yes, there may be question of existence.
So now, once you write supremum, but another write maximum.
Actually, both should be.
Because supremum is correct. In is arbitrary dimension. No? So you don't know. whether
Okay,
it can be
okay,
achieved
I
or
see,
not.
I
That's
see,
why it should be 50.
I see. Okay, yeah.
But probably this term, what are Ashim Naik, he has shown that this diamond norm that can be formulated as a calculating diamond norm of a channel that can be actually a SDB formulation can be. So it SDB formulation means we have some efficient method to calculate this diamond. Showing it was a non-trivial, he has shown.
Recently or
This is not recently.
Okay.
I remember when IMSC school was going, here.
for a general thing, sir.
General. HDB problem is for general.
No, it's HB, but for let's say some class of channels.
General.
Then this shooter retail, actually this is from shooter retail itself. Shooter, Winter and Renner, 2017. They actually introduced the concept of almost degradability and almost antidegradability. Remember, we will use almost antidegradability channel for our part. And they just bounded it from the above, this Q and P. P means the private information, Q means the quantum information. Quantum capacity of a quantum channel, P is the private capacity of a private channel.
So, for a quantum channel, that is epsilon goes to antidegradable, or the quantum capacity is upper bounded by private capacity, that is obvious. That is for any channel.
Yes.
Then there is this expression.
Yes. So actually, for our purpose, we are actually first upper bounding something, and then lower bounding something, and then we are showing that this is same.
For antidegradable, quantum capacity will be 0. No?
Yes.
Not antidegradable.
No, this is epsilon.
Epsilon.
No.
Quantum capacity should be 0. Degradable channel quantum. Degradable is additive.
Degradable.
Quantum capacity.
Because degradable channel, what you are doing,
No.
you are simulating environment states.
Antidegradable environment is simulating
State. So for antidegradable is 0.
Simulating the receiver. So if receiver gets some information, environment will also get the information.
Let's go back to the definition of so degradable channel. So I was asking whether degradable channel has a capacity or not.
Yes, degradable has a finite capacity, and it is additive.
Oh, sorry. Degradable is the simulation of environment.
Exactly.
Then it is possible.
Antidegradable is the other.
Yeah, sorry.
But epsilon has some non-zero, and that the important thing is they give the bound. So in terms of epsilon.
Are you using cloning argument that
Something they have in paper, they have written
that since an anti-degradable channel, whatever receiver is getting, environment also can get that. If there is some positive quantum capacity in this, then
so in asymptotic limit, actually,
kind of thing.
some dimension you will perfectly say no.
Both.
So that dimension will also go to the reproduce there.
So
That will violate cloning. No cloning theorem.
that's why what is almost anti-degradable channel, this must be bounded by.
Actually, this kind of bounds are this is very much useful because you don't know in general for capacity of a channel. Generally, in many things, this kind of bounds are used in order to bound the capacity. In order to compute the capacity, then you first bound and then you calculate.
B is the dimension of the B.
Yes. B is the dimension of the receiver. Means
But if you take epsilon goes to 0 here, so this H is what? H Shannon H.
yes.
So it will be 0.
No, it is coming 4, right?
Which is 0.
So H of 0, this is H of
This will become 0.
That must.
it must come.
Okay. Fine. Okay. Now, another concept is relative entropy of entanglement. What is relative entropy? So relative entropy between two states, rho and B, rho and sigma, is just defined as d of rho sigma is trace of rho log rho minus log sigma. Now, relative entropy of entanglement of a bipartite state rho AB, how it is defined? So, if the sigma AB is from set of separable states, mean that you just take the distance between rho AB and sigma AB, and you calculate the optimization. It's the relative entropy distance, entropy of entanglement of the bipartite state rho AB. Now, similarly, the relative entropy of entanglement of a quantum channel n lambda b is defined as you just take the again you can take the Choi form, means identity tensor lambda n over phi, and then you take the schema. So this is relative entropy of entanglement of a channel. And Isaac Lenio they showed that this relative entropy of entanglement is actually convex.
So for channel case, you have to again optimize about the state. So that need not to be always maximally entangled state will be. Some other state might be.
Actually, this is for choice state. This is same, right? Maximum integration is gives.
If this n is like a unitalmer, then
Then
maximum.
you can say that. Otherwise, that's why
Otherwise, it is non-maximum.
another hurdle is there.
Okay. Uh, okay. This is the complexity property of relative entropy. Okay, so now let's consider. I am still telling about this adaptive LHC because two LHC I will use the two LHC things.
So if the relative entropy of a channel is non-zero, then that channel has quantum.
It is upper bound. Relative entropy is upper bound of.
Because maybe some PPT entangled state is occurring. Then also relative entropy would be non-zero. You feed all entangled state and some PPT entangled state.
Okay, okay, yes, yes. This is from step.
Right? Relative entropy. Quantum capacity is
Something more
something
than that.
more than relative.
It's a channel, let's say it is PPD preserving channel or NPT breaking channel. I'm trying to say that. Then final state is all PPT.
Mhm.
Such channel will not horology channel.
Mhm.
What this means, and they have
Mhm.
used
They have quantum capacity.
separately.
Mhm.
They don't have quantum capacity.
Mhm.
But final state has some relative entropy because it is PPT and relative entropy is faithful.
Relative is a faithful measure of entanglement.
Entanglement, that's right. So PPT entangled state must have some non-relative entropy.
Mhm.
So there is distance between separate instances.
Mhm.
So it is then a lower bound.
Distance from step.
It's a lower bound.
No, relative entropy is
Relative would be
upper bound.
Which quantum capacity would be obviously less than relative entropy. So
This has final relative entropy. PVT, yeah. Okay, so now what is adaptive LHC? So let's say Alice has some quantum system. So A, which is his private, which is her private quantum system, and there are some A1, A2, AN, which she can send to some to the channel. And while she is preparing some row A1, A2, AN, actually Bob can assist. I mean, the task main aim is to distribute entanglement. So we want some entanglement distribution. Okay, so then first this A1 will be sent to the channel, and then this become for Bob's part. Means Alice is first holding A1, A2, AN.
These are practical index of quantum state.
These are quantum state.
index are classical, like A1, A2 are classical, then he is preparing some state, right?
So then, I mean, this itself is a let's say you can think of index or as well, but okay, it means one, two. You are saying that one, two, these things. Yes, yes. These are classical because they will use the classical communication.
No, but A1 is what are
These are some quantum states that.
no, but you are again giving row suffix.
This is you can think of as an overall some things means you have some all the things are quantum itself, and it's a some global something. You are sending this A1 subsystem or quantum subsystem to the channel.
This is a quantum channel, na?
This is quantum channel. Then Bob has this B1, and then again the state is updated that row. The actual subsystem become A is still there, and A1 will be B1 and A2 because A1 is transferred to Bob in this way. And in each step they can use 2 LHC. In this way, they can just finally distribute row AB with A with Alice and B with Bob. So, okay, like for to use how it will work, but you can just send it. But they use some concept of teleportation stageability because that concept is used uh, uh, in order to this adaptive LHC means you are using many round of adaptive LHC. So okay, let's first explain then I will say. Okay, so okay, so Alice has this subsystem A1, and Alice has So what Alice has this row, this A part, this bold A, which is let's say her private quantum some states which with her always, and some index A1 and A2. Index not index, it is also quantum state A1 and A2, and he has two copies of high class maximally intense. This where this index denotes that it is a 5 plus. It's a maximally intense state A1 and A2. And then with this part A1 and A1 prime, when this all are with Alice. Alice has many copies of this maximally intense state. With this A1 and A1, they measure of the base basis. This is like teleportation. So we are measuring on this basis, and then this another part is sending to the channel, and then this become B1, and this when you are measuring you give LCC, and you are getting B1 there, which after some whatever these channels uh, it's the rotation is, they will give some LCC and they will try to correct, and finally they will have B1. In this way they will distribute. The same things here also. So in this way you have, let's say, row AB, row A1 B1, which this has another A1. I'm just telling you just to understand. Let's say this has another A1 and A2.
So that first part what you discussed, that is just system A1 being teleported to Bob's lab, right?
Yes, but this is with not with
Some noise.
because you cannot have access.
Ah.
And then you have you can just use this kind of noisy, several copy of some noisy and state row A B are generated, and then you can finally distill, or finally try to some build some. I mean, you can try to build some good quality entangled state from this n number of states. So then yeah, so then using all these things, all these adaptive LOCC and many things, finally they want to distribute the entanglement to the channel. Which two LCC are also involved.
Can I say like that? Initial state was with Alice, row A, A1, A2. So finally it becomes row A, B1, B2.
Yes. So AB or B and B2, yes. Okay. So now we consider this channel. So this channel is a direct sum channel. So this is Alice's inputs in the reverse space. So this is identity, and this is the complementary of the dephasing channel. So the dephasing channel is 1 minus P rho P Z rho Z. It's complementary. So let's say when lambda equals to 0, then it's identity channel. When lambda equals to 1, this is the complementary dephasing channel. But again, this dephasing channel, dephasing. And for this dephasing channel, you understand that if P is 0, then it's perfect state. Also, P is 1, it's perfect state, means it's perfect. So the channel is like this. So 1 minus lambda rho, direct product lambda dp rho. So this direct product will help to calculate the several quantity, because these are two different Hilbert space. So if you have the access to different Hilbert space, you know that you can distinguish the every Hilbert space, and then you can calculate all things. So you can calculate the core information and everything for this simple channel.
So if P, let's say P is very close to 1 or 0. If P is very close to 1 or 0, then dephasing channel is good.
Good.
Then means its complementary channel is very bad.
Very bad.
And its probably capacity, quantum capacity is 0.
Quantum capacity is 0. Yes, when P tends to 0
or 1,
then it's
the dp bar will quantum capacity will be 0.
Anyway, it is actually just tracing out everything and some flag. And this flag is I mean, you can calculate the complementary channel from the isometric extension. And this is also in this Mark White's textbook.
If the dephasing channel is, let's P is equal to 0, P is equal to 0, then dephasing channel is nothing but the identity channel.
Yes.
And the complementary channel is nothing but the useless.
Yes.
So what you are saying is
Yes, man, this is symmetric.
That's why he's saying if P is very close to 0 or 1, complementary channel has no quantum.
no.
Okay, so then you can calculate the volume entropy of this channel. So this is just simple calculation of an entropy of the channel and this complementary channel. You can so this information.
Entropy of the channel is required entropy.
Well, this is yeah, means this is volume entropy, but you will calculate volume entropy. Yeah. The channel and complementary for the general state room. Actually, this is in different Hilbert space, right? So this will just 1 minus lambda this thing and lambda this thing in this way. It's very easy because these are two different subspace. And this HA is two dimensional and this is a qubit input, but HB is 4 because it has two different things with two different subspace.
So lambda is basically like a probability, right? With what probability which channel is actually. With some probability it is going into that subspace, with some probability with the DP bar, and with some probability it is going into this subspace with identity.
Identity and these subspace are orthogonal.
Subspace orthogonal.
This direct sum means
This, yes. Okay, so we can show that this channel is actually degradable for lambda range between 0 to half. For lambda is 0 to half means it is degradable, but for lambda greater than half means lambda 0 to half means it is more towards this part. So it is degradable, but for lambda greater than half, it is beyond degradable. Not degradable, not anti-degradable. Beyond degradable means not neither degradable, not anti-degradable. So actually, how we put we just take the isometry extension and then we show that there exists a map which can simulate the complementary channel can be simulated. So you can just it is very easy because you can think. Well, let's say okay. So what is the channel? Channel is for with 1 minus lambda over it is perfect state. With 1 minus lambda over it is a flat. So then if you just trace out the environment part for the 1 minus lambda part, if trace out the environment part, you will have the perfect state. And if you trace out the this part, you will have the this flat like this means for like that other part for the depolarizing dephasing and complementary of the different. Now we characterize the one-way capacity. So the one-way capacity we show that exact now we are in the degradable range means 0 to half.
that means it is additive.
It is additive. So if you calculate the co-information, then it is sufficient.
For that private also.
Private also same.
Private also additive.
Private also additive. Means, yeah, this is actually this for this degradable channel quantum and private capacity coincide.
No, yes.
And it is given by co-information by Departmental can. So we can calculate these things co-information. So how we just calculate co-information, which is the channel action of the channel minus complementary channel, and then we use some property that this channel this is symmetric with respect to x rotation and z rotation. So this IC n over rho is same as z rho z and x rho x.
Since you are showing how to calculate.
This is symmetric with respect to x and z. Then we know that co-information of a degradable channel is concave with respect to the input density operators. So we take this, we just take this rho plus half z rho z, and it is bounded from by above by these things. Concave, and it is also same for x. Now this is upper bounded by the co-information of the L lambda b, equivalent of the state diagonal in both this basis as well as this basis. So actually this maximization is over I by 2. Means the logically you have to find for which state the co-information you can achieve. So then we find that for I by 2, thus you can find the co-information and you can calculate for I by 2. Then you can calculate the co-information. So this is the one-way capacity of this channel. For two-way capacity, uh, this paper shows that actually this for two-way capacity. Okay, so we calculate the two-way capacity, quantum and private capacity as 1 minus lambda. But how? So this L lambda p can be prepared by adaptive LHC because actually you can find this paper, this where this adaptive LHC was teleportation stretchability was discussed. They showed that all the not all qubit channel, no, all the basic qubit channels.
So you were first talking about quantum capacity.
I'm talking about quantum and private capacity together.
Quantum capacity. Now you are saying quantum capacity along with that some one-way CC is
No,
there.
this is one way CC.
This is one-way CC. Another capacity is no CC is there.
No, two-way capacity CC is there.
That is one. I'm saying no classical capacity I will have. For communication I will have.
Okay.
Probably this one way and that will be same. That's why you are studying this one way is same as capacity.
Okay.
Q is equal to Q1. But Q2 might be greater than Q1.
Okay, you are saying that
Channel quantum capacity of a channel and one-way assisted capacity will be same.
same.
So one way and this without communication, its quantum capacity will be
Okay, there is some letter like that.
something might be there.
Okay. I mean, this should be known to me, but I don't know. Yes, maybe. I can ask and
Or
they
you
will
can
know.
see- you can see something.
Okay. So for now for 2 LOCC,
For these things, two-way becoming more.
actually that depends if whether you are using the range means range is this is symmetry means for another range you can find these things means 2A capacity is increasing, 1A capacity is decreasing, or here will show 1A capacity is increasing, 2A capacity is decreasing. Means we are saying that auxiliary resource is important.
So in this case, it is 1 minus lambda. Earlier expression was
1 minus lambda 2 minus
times
h.
a factor.
I will show the graph. So here how will we calculate? Actually, it was shown that this 2A capacity is actually upper bounded by relative entropy maintained. Relative entropy. Now you calculate the relative entropy. So this is a very simple channel. Identity answer n over this pi. N is actual dp bar identity, and you can calculate the supremum since means this bar is 0 because this is dp bar, and so it has no entanglement. This is identity, so it will be just this part will survive. And now we show that this is actually achievable. This is upper bound, but this upper bound can be achievable. How? By some logic that the encoder can send half of the maximal entangled state, and
For dp bar is the entanglement breaking.
yes, this is the entanglement breaking channel because it is just measuring on the 0 and flux, 1 and flux, and this is actually achievable because we know that direction structure. So whenever so actually, due to this directional structure, the communication parties can distinguish between the two subspace. So whenever they want to, I mean, they will just send a if, let's say you have a maximal interested and you have an identity channel, then you can establish on one EBIT or the channel capacity is one. Now that you do it 1 minus lambda probability because this identity is available with 1 minus lambda probability, and for the other case you just discard. So in this way you can achieve it. This is the 2A capacity. Okay, so then we show that if you just plot this expression, then you will show that this 1A capacity is actually increasing with. I mean, we take some parameters, but you can take some some particular p value. We check this thing for particular lambda value. You can check this thing. But we are doing some one parameter family. P lambda, let's say for lambda minus 1, and then we are showing that this can increase and this can decrease. Yeah, okay, 2A capacity is decreasing and 1A capacity is increasing.
And with lambda, you are plotting this.
Yes.
This is for a constant pi.
Oh no, P is also function of lambda there.
Actually, we parameterize this P. Means there are two parameters. P is the this thing, right? These things.
Understand, but I'm saying finally you go to your expression. No. Earlier expression.
These things.
Oh, HP is there. Oh, lambda and HP is there. Now P you make parameter in terms of lambda.
Yes.
Other term was other expression
Only
is
lambda.
Only lambda.
And then sorry, you can just parameterize, and then you can check that okay, no parameter is also necessary. Means we have checked that for fixed lambda, this you increase this and this way. But we parameterize and then say that okay, one capacity is decreasing, 2 capacity, and one capacity is increasing. And similar things for another parameterization.
Can you just explain this? Means if I increasing lambda,
If I increasing lambda, let's say now my noise parameter is lambda, then I increase lambda. This is one-way capacity. This one way capacity is lambda equal lambda is 0.25. This is 0.5. You can just make some
It is increasing.
reading.
1 to 2. Huh?
Not two. It cannot touch never here. So we have just show the diagram, not plot. It will not touch this line.
And 2A is decreasing.
2 is decreasing. When lambda equals to 0 and lambda equals to 0.5.
Which one is 2A? How to see it? How to
This one. This
red one is this one.
red one is 1 way, 2 way. And actually we have the lambda between this range, 0 and half.
2A. Oh, 2A is decreasing.
2 is the blue line, right?
Yes, yes. This one minus 100.
Let us do lambda function.
Yes.
So now if you go to the definition of this channel, lambda increasing means apparently noise is increasing.
Lambda increasing means lambda was with 1 minus 100 identity. Yes.
Lambda.
Lambda increase means noise increase.
But there is another noise there. So that you have to balance.
No, but when lambda increases, so P is
P is
4
function or
lambda
depend
minus
on lambda. P is also you are making on lambda.
So when lambda increases, P also becomes close to
When lambda increases, yes, then P, this channel is surviving more. But then again, you have to take
But
P.
whatever the thing is, if lambda increases, it is shifting from identity channel. Because
Yes.
identity channel is my perfect channel.
Yes.
It depends on the P value also. No, I'm saying let's say lambda is equal to 1. Then I have the okay. But if lambda is equal to 0, you have perfect channel.
Hmm.
Identity channel, no?
But then in case of lambda equal to 1,
Not 1. I'm saying now instead of 0, if lambda is equal to 0, lower value is identity channel. I now little bit increase lambda. So some part of the sometimes this my information is going to DP. But DP is some noise, whatever the thing is, it is not identity.
that depends on the P value.
P value.
P values, but that P
that
value
has
is
some noise.
that's some noise. It is not the identity. That's the right.
Can you go to the graph?
That's the right. It is not the identity. In some sense, what is its title? Noise is increasing, but my one way is with noise one way is increasing, but two ways decreasing.
This is only in the range lambda between 0.25 to this. Because lambda
But if you consider this is also for P value is for this curve, this P value we are considering when lambda.
No, your lambda bound in between them, that is due to P value. Because
Yes.
P dependence, that I understand.
Yes.
But within this region, that noise is increasing. That we can
Yes. Yes.
within this region, P value is increasing from from zero to some non-zero value. It is going.
Yes.
P.
Yes. And what is maximum is not when it is put here. How falling to 0.6.
So means
Point
when
two
lambda
something.
equal to 0.25,
But it
at
is-
that time it is completely useless channel DP value.
Yes.
But it is closer to 0. This part PP value is here.
It is 0, right? When lambda is 0.25, it is 0.
Yes.
0 means the complement is useless channel.
0 means
0 means it is identity channel, basically.
Dephasing.
But the complement is
Because you are taking DP bar
DP bar is completely useless.
completely useless.
But now when you increase P, DP bar is becoming more and more useful.
More
Yes.
useful, but still it is noisy channel. That's why he's playing this peculiar result. But still, noise is increasing.
so actually there are two noise. One they are actually playing the role. Okay. So,
And what about the
Means what I am saying is, can you go to that diagram of the channel? Yeah, this one. So when lambda is low, then you have identity here, and completely useless channel. But as you increase lambda, identity is destroying, but that is becoming more effective.
how to see whether there is only a are you asking something? No, but there is only two people.
Is there any question from there, Shayon?
Okay.
Okay.
Okay. So this is okay. So then we show that time we have. Hello. Is there any question?
You can take in.
No, sir.
Can you mute yourself?
So okay, I have 10 minutes. Okay, then I can just not skip these things maybe because these things one way and two way disk level entanglement and secret key. Actually, these things when we are going to study it for again for degradable channels, these are actually same for code information and upper bounded by relative entanglement. So the same quantity you can check and as you said the plot same things. So one disk level entanglement and one way key are same means that they also follow the same properties. So this one-way LSC protocol is how you can model it. Actually, it is you have some classical register. So there is some quantum instrument T, which is from A to A prime M, where M is the classical register, and the A prime and corresponding to each classical register. Let's say this is these M's are some orthogonal states, and corresponding to each M, you apply some city map from A to A prime. So this is, and then you just send this M through classical channel. So this kind of one-way LSC protocol was developed in this data winter. And if this is then this was this quantity is actually what the how much entanglement you can distill from the state to AB. This is actually calculated for this kind of maximization over all possible this instrument means all possible one-way communication strategy over this state rho AB, and you calculate the core information. And in this way, and okay, for degradable state, they show that these are additive. That is the point. So all that analysis will be followed. So I am not going to discuss these things as well. This is one of the key. Okay, so these two other things are same. And here we will actually use the this degradable states. So I define the degradable states. And then if we go the beyond degradable range, we show that if you calculate when this lambda is greater than half, then the channel is not degradable. And this coin function is actually super additive. Means for lambda greater than half, the two assistant and quantum and private capacity, actually this is the same argument, two-way capacity, but if you calculate the one-way capacity, you cannot calculate the one-way capacity because the core information is super additive. So you take one unit of the channel, it is some quantity, and two units of the channel, it is some other quantity. But this one unit of the channel is actually lower bound because at least that amount of quantum information they can send. So then we use this epsilon anti-degradable property and we take suitably a anti-degradable channel and we take the distance between this and this and we take the upper bound of the channel. It's this how to characterize the beyond degradable range. So we take a upper bound, sorry, we take a upper bound and we take a lower bound from the one inch of the channel and upper bound from these kind of things. And then you just plot upper bound and lower bound. Okay, two capacity is always decreasing. And if you plot upper bound and lower bound, then we show that let's say there are some channel, some point xn and xn. So the upper bound of at xm, okay, lower bound of xm and the upper bound of xn is actually same as lower bound of xm. So at least xn, the capacity for xn is less than xm. So this is actually monotonically decreased. Means although we cannot comment here from the continuous things, but at least there are infinite. You can go in this way, and infinite number of sequence of points are there for which you can just predict that one capacity is increasing from this argument. and then we this kind of same kind of things are also holds. Okay. Now, okay, so let these things is classical vector channel. What is classical vector channel? So classical vector channel is, as you know, that you have a channel from sender to receiver, and how much information if you tap the wire, this wire, where through it I'm going to send the information. Then how much information is leaking to the environment. So we took this channel. So Alice is transmitting information to Bob and it through a noisy classical channel, and her task is to send information encoded in such a way that Bob can decode, but it learns nothing about the message. That's our aim. So we then characterize this one-way capacity and two-way capacity. So okay, so then this is an input register X, and the channel is like that.
Channel is quantum.
Channel is classical channel.
And you,
Actually, for classical memoryless channel, feedback does not help.
classical channel and you are interested.
In classical private information, private classical information.
And you are saying one way, two way, that what like that.
Yeah, let's see the nuance because when we analyze, you can just visualize. So this is also two part. This first part, okay. So this channel, this Z is going to environment Z1, Z2, and Y is going to the receiver. And this is with 1 minus lambda volt. Okay. Okay, this part, this one part means there are two sub channel. So this is one channel, this is second channel. This first channel is with lambda probability, this part, and this is with 1 minus lambda probability, this part. So channel is like that. So let's this is some Markov chain from X to Z1 to Y1. Z1 is inside, means Z is towards the environment, the H cover. The channel is like that. So we have some classical index X. You are to calculate the probability of YZ given X. So the channel is like that. So all information goes to X, SZ. Means whatever information is with the sender, all information goes to Z, the delta XZ. But from Z to Y means this is a binary symmetric channel. So while binary symmetric channel, it will fit with probability 1 minus P or P. This is symmetric. So 0 goes to 0 with P and 1 minus P and same thing. This is binary symmetric channel from Z to Y. And the other channel is like that from X to from XY is delta means all the information of X goes to Y, the receiver, and this is a random. Means for the environment it is going randomly. Then okay, so this is the channel. So we first observe that this channel N lambda P is degraded. Actually, this is degraded from Z to Y. I am not talking about this channel. I am talking about overall channel. So overall channel can be shown that it is degraded. So if it is a degraded channel and a channel degraded from X, Y, Z, it follows the Markov chain, means X to Y to Z. It's like the same concept like classical case, quantum case, X to Y to Z. So there is some stochastic matrix map that allows Bob to produce Z from Y. So for degraded channel, this capacity is given by the simple expression. This is the classical private information. So IXY is the mutual information between sender and receiver and information in the sender and environment. And you can optimize our PX. This is the expression you have to calculate. So then you can just calculate these things. So what you will do, since it is a direct some things and then some broadcast parameter lambda. So this is just lambda with this for the first part. This is with lambda probability, and second part with 1 minus lambda. So this lambda, the information with the first part means the private information of the first part, the 1 minus lambda private information of the second part. And as you can understand that for the second part, let's consider for the second part. So what is xy2? So this is 1, right? Means whatever it is having, it is that is receiver is having the same things. So it is actually the hx is the input distribution you can calculate hx. And for ixz2 means for the second part it is random, so it will be 0. And similarly for ix1, you can calculate that this for the binary symmetric channel. actually you can write the p what is p x y z given x. So binary symmetric channel, you can, for 0 it is p, for 0 p 0 1 1 minus, you can write, and you can calculate this thing as 1 minus lambda x minus n. And this is maximized when x is uniformly distributed. So this hx is 1. So then you can calculate this thing as 1 minus lambda 1 plus hp. So you can calculate the one-way capacity of classical vector channel as this. Now the two-way capacity, okay, this is by some inspection. So how you will get this two-way capacity is again 1 minus lambda. How?
Two-way capacity means now feedback.
Now feedback is allowed. So then let's see how the logic. So we can first, so that we can achieve this 1 minus lambda. So how? So then since for the second part, py to x is delta xy, and this z2 is independent of x because it is random. So when Bob receives y1 part, she will just discard. Okay, when Bob will communicate to Alice that I got from this portion, so just discard it. And when Bob will get this part, y2 part, then she will just reports back to Alice that, and then we already get y2. So Alice and we avoid further transmission so that it cannot learn anymore. So they will stop. So when they will get this part, they will communicate. When they will this part, they will stop. In this way, you can achieve that. Okay, and this is happening with 1 minus lambda body. You can get the 1 minus lambda. And the converse is also by inspection that if Alice sends more than 1 minus lambda bit of, I mean, this is same logic. And if Alice is sending more than 1 minus lambda information, then there is some possibility that it can learn because from this structure. So in this way, this 1 minus lambda is the two-way capacity. And then if you plot again these things, two things, then you will see that this one-way capacity is increasing and two-way capacity is decreasing. So actually, so the result is like that. So if you have some noise, some channel, some lambda parameter noise parameter. So when the noise parameter is increasing, which this let's say this y denotes the noise parameter, it is increasing. Then for one-way capacity, the message is getting transferred, means more transparent, and for two-way capacity, it is more noisy. So for this two-way capacity, assisted capacity is actually depends on the the capacity of a quantum channel depends on the context. So whether you have one-way capacity, one-way LCC or two-way LCC, and this is actually we can I mean one can say that actually this is nothing but some superadditivity phenomena or some, I mean what all earlier results holds are due to superadditivity of coherent information. But here since we have already shown that this is hold for degradable channel, so discarding the possibility that noise resource contextuality is a byproduct of coherent information superadditivity. So this is the result, and this actually this channel is very similar to the this channel by introduced by Lensky and other superadditivity 2017 channel, which is actually not direct sum but almost similar. And so this channel was also analyzed experimentally, so it is also, it can be done because it is just complement of that channel, and it can be done by experiment. It can be simulated by experiment as well. Okay, thank you very much.
The question.
So can you go to that like first figure, that 4 lambda minus 1, that one?
For this one,
This one. So is this behavior that one way is increasing but two way is decreasing, is this also there for some constant value of
yes,
p?
that's what
Then that is more
more.
interesting.
No, but yeah, means
And also, finally, I'm saying this is not due to coherent superactivation of coherent information. I'm saying more thing is this even in class for classical channel you are showing.
okay.
Classical WhatsApp channel you are showing something here.
Yeah, so the result was that feedback cannot help for classical memoryless classical channel, means which are Markov chain. For that kind of channel, oh sorry, uh, not macro channel is degraded channel. No, for memoryless classical channel. If you teach a memory classical, then the feedback cannot help. That is from Shannon itself. But yes, this is classical. But it's wiretap channel. Means we are interesting on the private information. So this is a little bit different.
Another thing, probably you know that from earlier the first channel is construction. This one. So you take this is dephasing, no?
Hmm.
Recently I was telling you that Watts and Devillium has an interesting
Complementary channel has.
of depolarizing channel has always non-zero capacity. So instead of dephasing, if you take complementary of depolarizing, something interesting and it need not to be what is called degradable, because without degradable, if it is not degradable, still you can analyze using this result of tool, Renner, all this kind of.
Yeah, actually, the main thing is, I mean, people use the simplest channel, means so that they can analyze the capacities. If it is little bit complicated, then capacity cannot be analyzed.
But you can have some upper
Some
bound,
upper bound.
using epsilon
Mhm.
epsilon anti-degradable concept. Might give you something.
Okay.
Civilian what to construction.
Okay.
Okay, if there is no question, then thanks.
Okay. Thank you.